All right, welcome back for day 2 of Unit 9. Today we're going to talk about exponential tables and equations and how to interpret the different pieces and parts of an exponential growth or decay function and how to write an equation given the context of a problem. So, in an exponential, what you're going to be basically needing to find, very similarly to the equation of a line. In the equation of a line, you need something called the slope and the y-intercept. And actually, for an exponential function, you need the y-intercept, just like before, but you need something called the growth factor or the decay factor. So it's not the slope, so I don't want you to think it's the slope because remember, that's a constant. The growth factor is what you multiply by, or if it's a decay function, the decay factor. And so in our kind of standard form of an exponential function, there are two parts. We have the coefficient out front and we have the base of our exponent. The coefficient out front is going to be known as the y-intercept, okay, so the y value when x is 0, or if we're talking in terms of like a real world kind of problem, the y-intercept is going to be your initial amount. So how much money you put in the bank, how many bacteria you started with, anything like that. And then the base of our exponential, either our growth or decay factor, depending on which type of situation it is, that's going to be what we call the common ratio that you're multiplying by. So whatever you multiply by to either grow your function or decrease your function, that's going to be the base of your exponent. And then obviously don't forget to throw the little x in the exponent because that's what makes it an equation. Now, we're not always going to use an x. Sometimes it'll be a t if we're representing time and things like that. So let's take a look at number 1. It says the breakdown of a sample of a chemical compound is represented by the following exponential equation. And I know it's an exponential equation because the variable is in the exponent. P of t represents the number of milligrams of the substance, and t represents the amount of time in years. Is the function p of t representing a growth or decay? So do not get distracted by that 300. 300, remember, is just your vertical stretch. The base of your exponent is what tells you if it's growth or decay. And since it is less than 1, since 0.5 is less than 1, that's going to give me a decay function. So that means, that gives me a little bit of information here. That means the breakdown is decaying. So this chemical compound is decaying over time, which is good. What is it decaying by? Well, what does the 0.5 represent? That is our decay factor. That means for every year, half of the chemical compound kind of decreases by. So the decay factor is the fact that the substance decays or cuts in half every year. So then what does the 300 represent? Well, the 300 is the number out in front, and we said the number that's in front of our decay factor is what we call the y-intercept or the initial amount. So we must have started at the initial amount of this chemical compound, whatever it is, was 300 milligrams. Okay, so you can actually get a lot of information just by looking at the equation. So let's take a look at number 2. Some banks charge a fee on a savings account that are left inactive for an extended period of time. The following equation represents the value y of one account that was left inactive for a period of x years. What is the y-intercept of this function and what does it represent? So if you go back to the top of the page, we know that the y-intercept is that front coefficient. So that means our y-intercept is 5,000. So A and B are totally out. But then it goes on to ask, what does it represent? 5,000 must have been the amount of money that was initially in the account, because remember that y-intercept is also representing the initial amount that you start with. All right, well, what if I give you information in a table, not maybe in a context, but just in a table? Does each table represent an exponential function? So we're basically going to say yes or no. And then can we write the equation of the function for each table? So let's take a look at letter A. If I go from 0.25 to 0.5, 0.5 to 1, 1 to 2, 2 to 4, I hope you start seeing a pattern. And that pattern means I am multiplying by 2. That is my growth factor. So if it is growing by a factor of 2, my growth factor, remember, is the base of my exponent. The y-intercept is when x is equal to 0. So my y-intercept is 1. And that would equal my equation. So if that's what you think your equation is, and I know that looks kind of funny because I wrote my 1 like that, so you could write it this way too. If you want to double check yourself, if you're not confident, or if you are confident and you still want to double check yourself, that's fine. 1 parentheses 2. And I usually have one student that says, do I have to write the 1? You don't have to write the 1, but it's a good habit to get into. But there you go. The table matches perfectly. So let's try a new one. All right. Looking at your y values, y 9 to 3, 3 to 1, 1 to 1/3, 1/3 to 1/9. Now remember, these numbers are clearly reducing. So we're definitely talking about a decay. And to get from 9 to 3, and then 3 to 1, and then 1 to 1/3, I know what you're thinking. You are thinking divide by 3. But I don't know how to represent divide by 3 when I have to write it as an exponential. So that means I am multiplying by 1/3. So when I write my equation, the base of my exponent is a 1/3, and my y-intercept is a 1. And again, you can check in your calculator if you'd like. So now let's put that kind of knowledge into a real-world context here. An application developer releases a new app to be downloaded, and the table below gives the number of downloads for the first 4 weeks after the launch of the app. Write an exponential equation that models this data. So the first thing we need to do is, it's telling us it's exponential. I need to figure out by how much is it growing. And clearly the numbers are going up, so I know it's exponential growth. It would be bad if they developed an app and it was losing users. So how do I figure this out? 120 to 180, 180 to 270. So again, if you take out your calculator and you actually do week 2, so let me go to my home screen. If you do the users on week 2, which is 180, and divide it by the number of users from week 1, it looks like it's growing by 1.5 times. Let's confirm that by doing week 3 divided by week 2. It should be the same amount every single week for it to be considered exponential growth. So this is being multiplied by 1.5 over and over and over again. So we know when we write our equation, we know the base of our equation is a 1.5. But for us to be able to figure out our y-intercept, the number that goes in this spot, I need to know my y-intercept, which is in week 0. So that means I need to work backwards and figure out what number came before 120. So to figure that out, I actually am going to do 120 divided by 1.5, or 120 divided by 1.5 in my calculator. 1.5. All right, let's see. So 120 divided by 1.5. And so that means they must have started with 80 users before they decided to launch this app. So 80 is my y-intercept. All right, well, what if I only give you a piece of the table? I still needed the same 2 things. I need a y-intercept and a growth factor, or decay. So let's use the knowledge of the fact that this is an x and this is a y, and this is an x and this is a y. So 2, 4, 3, 16. And I'm just going to work backwards, essentially. So this is the information that they gave me. Let's use that to work backwards. So to get from 4 to 16, my growth factor is multiplying by 4. So that's going to be the base of my equation. And then again, all I need to do is find my y-intercept. So if I want to work backwards, 4 divided by 4 would be 1. And then if I divide by 4 again, I get 1/4. So there's my coefficient, and there's my equation. Let's try another one. So if in number 6, I start with the information they provide me, which is 2, 14, and 3, 7, well, I need to go all the way back to 0. To get from 14 to 7, I'm thinking divide by 2, but that's not how I'm going to write it. I'm going to write multiplies by 1/2. So it is a decay function with a decay factor of 1/2. And let's use that and flip that. And so to go this direction, I need to basically say, okay, what cut in half gave me 14? Or 14 times 2 is 28. All right, and then what cut in half gave me 28? So 28 times 2, which is 56. So that is the initial amount that I must have started with. All right, well, let's see if we can continue doing a few of these, and then I'm going to show you a little trick for 8 and 9 in your calculator, and then I believe then we're almost done. Which function is shown in the accompanying table? Okay, so let's take a look at our chart. 1/9 to 1/3, 1/3 to 1, 1 to 3. Now it's getting a little bit more obvious. 3 to 9, 9 to 27. Okay, clearly that chart is being multiplied by 3 over each step. So if it is being multiplied by 3, that is exponential growth. You want to know it's not? It is not a linear function. So get rid of 1 and 2. Those are both representing lines. Notice there is no exponents in 1 and 2. So now let's take a look at options 3 and 4. Literally the only option here that has a variable in the exponent, which makes it an exponential, is option 4. And to confirm, our y-intercept is at 1. So we would have written this as our equation, and that matches perfectly with number 4. This is a cubic, so we know that that's not the answer. All right, number 8 and 9 are very similar. It says a laboratory technician studied the population growth of a colony of bacteria. He recorded the bacteria every single day. And a part of the table is shown below. Which function could accurately model the data? Here's what I'm noticing, again, similarly to the last one. 25 to 15,000, over 15,000, and then from 15,000 over to 9 million. Clearly that does not increase by adding the same thing over time. So anything that would create a line is out. So 3 and 4 are out. Both of those are just linear functions. We need an exponential growth function. All right, so now that we have it narrowed down to 1 and 2, if you look at option 2, see how it has that +1 in the exponent? That makes me a little nervous because that means we know that means it's being shifted to the left 1. And I don't know how to do that when I'm writing my equation. So here's what I suggest. You take out your calculator. You have it narrowed down, so you have 2 options here, right? So if I take out my calculator and I go to my y equals screen, and let's start with just option 1. Why not? Start there. Raise it to the x power, so 25 to the x. Go to your table of values, and let's see if it matches. So day 0, it says there should only be 1 bacteria. And clearly in my chart over here, it tells me I should have 25. So that one's already wrong. So now let's go back to our y equals screen and check option 2. So +1. Okay, go back to your table, second graph, and go to day 0. There it is, 25 bacteria. Go to day 2, which is what the chart says. Day 2 should have 15,625. That's exactly what my table in my calculator says. So obviously option 2 is the right answer. So I had some knowledge to narrow down my options, and then I used my calculator to kind of finish the problem up. So let's do the same thing in number 9. 9 to 17, 17 to 65, oh actually they skipped a number here, 65 to 129, 129 to 257. Okay, so already I can tell, going from 6 to 7 and 7 to 8, here to here, there is no way that that function is adding the same amount every time. If it's not adding the same amount, then any linear option is out. So anything that would make a line is gone. So now I'm between option 1 and option 3. And yet again, we have this shift up 1, and I don't know how to write the equation that way. So you know what? Let's go to our calculator, clear it out, type in 3 raised to the x power, that's option 1, and see if it matches our chart. So at 3, at 3, it's equal to 27. And over here, it's 3 is equal to 9. So let's make sure. Clear that out. 2 raised to the x power plus 1. Go to your table. And at 3, there it is. It's equal to 9. 4 is equal to 17. I think we found our winner. There it is. All right, last example. Almost last example, we're almost there. Bacteria population y after x days can be represented by the following exponential function. Write an equation. Okay. We can do that. This is an x and this is a y and this is an x and that is a y. So 0, 100, 1, 200. And to write an exponential function equation, we need two things. How do I get from 100 to 200? Well, I multiplied it by 2. So my equation would be 2 to the x, and then I also need, remember, a y-intercept, and they actually gave it to me in the problem. So I started with 100 bacteria. Using this equation that you came up with, find how many bacteria you would have after 6 days. So I could either keep extending this chart out, but I think once I have an equation, the easier way would just literally plug and chug. Plug in that 6, type that in your calculator, and I believe you get 6,400 bacteria. Number 11, again, very similar. I gave you a chart, a graph to take a look at it. I also gave you the table of values. I'm going to use my table of values more than the graph option. Write an exponential function that would represent the population. So here we go again. Find your equation. What is your growth factor in this case? To get from 3 to 12, 12 to 48, those are probably the most obvious ones to figure it out. I am multiplying by 4. And they even gave me my population. I started with 3. Using your equation, figure out what your population would be on the 5th day. So I'm going to plug in a 5 for x. Oops, that should be a 4. I'm going to plug in a 5 for x. And if I type that correctly in my calculator, my population grows to 3,072. Last question for today. It says write an exponential function, but this time I can only use the picture. This was actually a question on a Regents exam a few years ago, and I'm going to use the same exact strategy I've been using this whole time. So take a look at your graph. Find a few spots where it appears that it crosses at a really nice point. So it looks like it crosses at 2, 1, 3, 2, 4, 4, 5, 8. And remember, we always need to find our y-intercept. So if I can figure out these 4 points, there is no reason why you can't look at that pattern, 1 to 2, 2 to 4, 4 to 8, and notice that it's multiplying by 2. And if it's multiplying by 2, we know that that's our base. All we have to do is work backwards 2 spots to find our initial amount. So if what came before 1 would be a half, and what came before a half would be 1/4 or 0.25. However you want to write it, I would accept either answer. And so did the Regents, but that means our y-intercept here is 0.25. All right, that's it for today. I'll see you next time.